Hi, now we move to the chapter 4, GPS for the Earth observation and the GIS. So basically, in this chapter we will talk about the GPS. So what does GPS means? GPS, or the name is the Global Positioning System, is a satellite-based navigation system which consists of 24 orbiting satellites, which each of them makes 2 circles around the Earth every 24 hours. And these satellites transmit 3 bits of information, which is the satellite number, its position in space, and the time the information is sent. And the signals are picked up by the GPS receiver, which uses this information to calculate the distance between it and the GPS satellites. So basically, here it explains that GPS is a satellite system where the satellites is orbiting the Earth. There are 24 of them, and now we have more and more, such as GLONASS, Eurostar, and we do have this Beidou from China, and Japan and Korea will follow suit to launch their GPS satellites. And until now there are more than 60 satellites around the Earth, and it has different names such as what I mentioned before. And those satellites, we heard the rumors, or we heard the hearsays, these are the urban legends, says that GPS, the satellites can detect your location. This is not true, because basically the receiver is the one who receives the informations, which is the satellite numbers, its position in space, and the time of the information is being sent. And those signals are being picked by the GPS receiver, such as our phones, and those information will be used to calculate the distance between the receiver, let's say it's our phone, so the receiver, and also the GPS satellites. Therefore, those receivers are the ones who come up with the location on the Earth, not the GPS satellite. So what is basically GPS? It is originally, the system was designed only for the military applications. So since 1970s it was around, but being used entirely by the United States of Defense, of course being subscribed by other countries, until late 1980s it started to be used for the civilian. And back in late 1980s to early 2000, the GPS that being used before doesn't have any accuracy as accurate that we have now. Before this, the accuracy is much worse, about 100 meters accuracy, which is useless for the civilian use. And until year 2001, the United States of America has decided to uplift the restrictions on the GPS so that the civilians can enjoy the accuracy of the GPS that we have now. So now we are looking into the segments of GPS. There are 3 segments of the GPS. The first one will be the space segment. The space segment, it consists of 24 satellites, and now more than 24, which circling the Earth at 20,200 km in altitude. It is quite high. Basically, it's higher than the remote sensing satellites, and also it is almost the same height as the telecommunication satellites, broadcasting satellites. And this high altitude allows the signal to cover a greater area. That's why we enjoy the receptions of the GPS satellites 24 hours. And these satellites are arranged in the orbit, so a GPS receiver on Earth can always receive a signal from at least 4 satellites in any given time. Why you must have at least 4 satellites? Because it is required to have at least 4 for the GPS receivers to calculate the triangulation. You know, those Pythagoras theory things, in order to estimate the location of the receiver. So remember, the keyword is to estimate. And each satellite transmits low radio signals with a unique code on the different frequencies, which allows the GPS receiver to identify the signals. Meaning to say here, those satellites, they have their own code, the numbers, the unique numbers of the satellites, and the GPS receiver able to identify for those signals that have been received whom sends the signal. And the main purpose of these coded signals is to allow for calculating the travel time from the satellites to the GPS receiver. So what are the speeds of those travel time? So basically the travel time is about the speed of light, and this speed of light will be multiplied with the time equals to the distance from the satellite to the GPS receiver. So meaning to say, the time travel multiplied by 100,000 kilometers per second, and you will get the distance of the satellite to the GPS receiver. So basically it's about microseconds. And since these are low power signals and would travel through solid objects, therefore it's important to have a clear view of the sky. And this explains why GPS receivers will not able to get any signals if the receivers are inside the building. So bear in mind that if you want to have a good signals, please make sure that you are out from the building, and also to ensure that you have a clear view sky. The clouds or heavy rains will more or less will disturb the signals to the receiver. And these are the GPS nominal constellations, where there are 24 satellites in orbital planes, 4 satellites in each plane, 20,000 to 200 km of altitudes, and more. The number 2 segment is the control segment. Okay. So the control segments is basically will track the satellites and provides them with the corrected orbital and time information. What does it mean by here? So basically there are 4 unmanned control stations and 1 master control stations which being built to send or to receive the data from the satellites and then sends the informations to the master control, where it is corrected and sent back to the GPS satellite. Bear in mind that those satellites, they only sends the signal to the receiver. Therefore, there must be a mechanism to do some corrections of the time of the informations, right? And this is the task of the control station. And the idea of this control sections is because of the GPS satellites is prone to be disturbed or prone to be swayed by the gravitational force due to the movement of the Earth, the orbiting the satellites, the gravitational force that being created by the satellites due to orbiting of the Earth, the effects of the moon, the effect of the moon which orbits the Earth as well. So they will have some sort of the gravitational force trying to pull and push the satellites from its designated location. Therefore, what happened? And remember also, sun do also have a lot of gravitational force, will more or less will push and pull as well the satellites from its supposed to be the location. So what happened? The movement of the satellites will affect the signals being transmitted due to what we call as a time travel from the estimated time, estimated location and time by the control station and also the actual location and time. This will introduce some errors in the GPS, which we call as a ephemeris data error. Okay, and we will talk this more about this later. And the last one will be the user segment, where the user segment consists of the users and their GPS receiver, and the number of the simultaneous user is limitless. Therefore, even though 7 billion of people around the world uses the GPS on the same time, the GPS satellite doesn't have any effect on it. So these are the control segments, as I explained before. Data to the control stations, to the GPS, and data from it, so on. And the user segment, cars, planes, and also ships uses GPS widely. Alright, now we look into the how do the GPS works. So when a GPS receiver is turned on, it first downloads orbit informations of all of the satellites available within that particular region. And this GPS receivers knows the precise location of the satellites in space. How did they know it? Because GPS receivers have the pre-downloaded ephemeris data from the satellites. Okay, and it needs to know the distance from each satellite it's receiving a signal from. Therefore, the distance will be calculated by the receiver, which is multiplying the velocity of the transmitted signal by the time it takes the signal to reach the receiver. And this velocity is the speed of radio wave, which is 30,000 km per second. And to determine the time part of the formula, the receiver matches the satellite transmitted code to its own code. So there are some verification takes place between the receiver and also the satellites. And by comparing them, determine how much it needs to delay its code to match the satellite's code. And this delay time is multiplied by the speed of light to get the distance. So the GPS receiver clock is less accurate than the atomic clock in the satellite. So each distance measurement must be corrected to account for the GPS receiver internal clock error. That's why for the ground stations, it will send the corrections to account for the GPS receiver internal clock error, and this will ensure the accuracy of the system itself. So the GPS signals frequencies, the fundamental frequency which give you the identification of the satellites is the fundamental frequency, which is 10.23 MHz, and then there are two carrier frequencies, L1 and L2. There are two codes, which is the CA code and the P code. So these codes carry information from the satellite to the receiver, and the GPS receiver will decrypt those informations and come out with the calculations, and from those informations of the calculations will determine the coordinates of latitude and longitude on the Earth's surface. And those signals are spread kind of spectrum. Therefore, it is harder to jam, in which the frequency of the transmitted signal is deliberately varied. So now we look here. The L1 carrier will be mixed together with the CA code and also the navigation systems to come up with the L1 signal, and this is what the receiver said. However, and this is mostly for the recreation GPS, such as the handheld GPS, Garmin for example, the car GPS, ship navigation, and more. However, for the commercials, they will using the L1 and L2, which will increase the accuracy by centimeter scale. And for the military use, they are P code, which is the encrypted code to increase the accuracy more. And nowadays we do have the L5 code, which is for the civilians, where it increases the accuracy of the satellites into a sub-meter accuracy. And those codes are the streams of the binary digits known as the bits. If you familiar with the computer systems, bits 1010, those kind of numbers, or chips. And this is also called as a pseudo-random noise codes. And this codes basically is modulated, amplified by the frequency or amplitude modulation. Therefore, the code stated +1 and -1, and they are the source code for L1. However, P code both available for L1 and L2, and those phases are being modulated by the system to give the informations. Now we look into the CA code. It is a stream of the 1, 0, 2, 3 binary digits with the numbers of 0 and 1s, and it repeats every millisecond. So what does this CA code brings is it enables the identifications of the satellite, and it is referred to all users. And sometimes it was called as a standard position service, and before year 2001 it used to be degraded by the selective availability. However, P code is 10 times faster than the CA code, where it has 38 segments for the satellites, and also the part of the message being broadcasting, and this is called as the precise positioning services. And for the encryptions, this code only can be encrypted by using the military grade tools, meaning to say this code specifically for the military use. And nowadays we do have this L5 code, okay, and other national military codes will be on the way, I think. Until now there's no news, but L5 code will be make its way in year 2020 and 22. So for the time segments, time systems, so each satellite has a multiple atomic clocks where it is used for time and frequency on satellite. Do you know what does it mean by the atomic clock? So basically, atomic clock, the time being counted from the atom fusion. So meaning to say there's a half-life for the atomic fusions, and this half-life is being used to determine the seconds or microseconds of the clock. However, the GPS uses the GPS time, where it started on the 6th January 1980s. It is not adjusted for the leap seconds, and it was used to time tagging GPS signals. However, after that it will be coordinated, it will be what we call it, it will be synchronized with the coordinated universal time, which is based on the international atomic clock, and this atomic clock adjusted for leap seconds, yeah, and it is based on the Earth rotation time. Okay, so what happened? There are some offset between the GPS time due to the satellite and the receiver clock errors. As we see here, satellite using atomic clock, GPS using GPS time, and it being synchronized through the UTC in order to come up with the corrected versions of the time. And now we look into the GPS errors and biases. Of course, as I explained before, there are some errors being introduced due to the environment factor, most of it due to the satellite itself. But remember that within the atmosphere, due to the different thickness of the gaseous molecules, yeah, clouds, rains, buildings, and more, of course, the position of the satellites, the terrain, and so on, this will also introduce the error and biases. And there are three types of error. The first one, satellite errors. It differs for each satellite. The second one, transmission errors. It depends on the path of the signal. And the third one, receiver errors, different for each receiver. Okay, so basically all of these error and biases cannot be modeled, will degrade the data. Taking example the satellite. if the satellites there are some equinox phenomena which introduce a slightly stronger gravitational force over the satellites, it will tend to pull the satellites a bit away from its orbit. Therefore, this, because of the satellites, it gives the informations differently. Time travel and the position, estimated positions from the almanac is different. What happened? There are some error introduced due to the time and estimate locations. Therefore, what happened? The readings of the satellite will be swayed a bit. And of course, the environment, if they are raining, heavy rains, thick clouds, you will see the satellites, the signals of the satellite will be degraded as well. And also, if you are inside the KL, let's say you are driving in the KL city with a lot of skyscrapers, you will see that the GPS somehow will shows a different position, or can we say that it gives you some haywire of the locations, as opposed to if you're driving in Kuching, less skyscraper, so the position, the locations that be given by the GPS is much accurate. And of course, the receiver, along the time, the technology advance, change, become better and better. So the GPS that you buy over in year 2010 and 2020, the accuracy will be different because of the betterment of the technology, the advancement of technology, and also the speed of the microprocessor inside to process the data, as well as the receiver's quality. So these are the things that can affect the quality of the GPS. And the receivers that are close enough have very similar errors and biases. So data can be combined in ways to mitigate the effects of error and biases. And there are some different kind of data, different kind of techniques can be used. Either you can combine data from two receivers over a satellite, okay, or you can combine you can combine more data, more satellite data. And in practical, we combine either one receiver, we have to have at least 4 satellites, which is able to reduce the atmospheric error, as well as for the industrial applications, we use 2 GPS receivers and more satellites until 20, because we want to increase the accuracy, to reduce the differences until 0 and more, so that the accuracy will be much better. And also the GPS nowadays, our phones have L1, some of the new phones have the L5 as well. They started to use the L5 processor, signal L5 receivers to eliminate the effects of the ionosphere. And the commercial, they have L1 and L2 data. And also, you also might see that how the surveyors are using the commercial GPS, which is having the L1 and L2. And also they use the long wide land observations, where they put the GPS, they have the base stations, okay, and also put it for a couple of hours to increase the accuracy and more. Alright, now we look into the GPS error. Okay, there are atmospheric error, multipath, satellite geometry, measurement of noise, the ephemeris data, and the satellite clock drift. Now we look the ionosphere and tropospheric reflection, which is the atmospheric effect. So basically, due to the differences of the thickness of the atmospheric layer, the signals will be refracted. As you can see here, there are some refraction over on the ionosphere and also troposphere, where it will give a slightly difference of the angle of the satellites and the position itself. Therefore, it will introduce the error. Multipath, as I said, buildings will introduce this multipath, where the receiver will detect 2 signals on a different time the time frame, okay, to the same difference, the same signals from the same satellite into different time, where the direct one will be slightly faster than the distorted one. Therefore, it will also promote the error. And the satellite geometry as well. So basically, it's about the geometric dilution of precision. This is about the positions of the satellite on the sky. If the satellites are evenly distributed on the sky, it will give a better measurement. If it is slanted or slightly focused on one area only, it will give you lesser less accurate of the measurement. Okay, it's like this. This is the good satellite geometry, which is evenly distributed. Okay, while the poor satellite geometry will be something like this. This in Malaysia, this phenomena happens on the morning until afternoon, and started when it goes to after 2 p.m. and until midnight, until night, the satellite position will be like this. That's why you can see that the differences between if you use this GPS on the morning and also on the evening, the accuracy will be different because of this satellite geometry dilution of precision. Okay, and of course it refers to the position on the horizontal and vertical, where it will give you the effect on the latitude, longitude, and also the altitude. So all of these will be determined and will come up with the PDOB values. Before this, in the pre-2003 GPS, they have the readings of the PDOB, but nowadays there are no more in our GPS. But for your information, these PDOB values, usually what we do, we wait for the value less than 4 to ensure the accurate measurement or accurate readings. But most of time now our GPS is quite good, therefore most of time it shows the excellent numbers. That's why nowadays the new GPS, they doesn't have this kind of application to identify the PDOB. And the ephemeris data, which is a list of the satellite positions as a function of time. Okay, this is what we call as an almanac of the GPS locations on the sky. This almanac will be released by the United States of Defense and as well as NASA. It is free to download. Our GPS receiver have pre-installed in it. Every time we open the GPS, it will update the informations. And those satellites, those ephemeris data is individual data for each satellites. Okay, so what happened to this data? Okay, it able to identify the orbital error, where the position of the satellites obtained from the signal informations is a prediction. Therefore, this ephemeris data that we download or we install inside the GPS is a prediction of where the satellite should be at a given moment. But in reality, it will be slightly different due to effects on the gravitational force, as I mentioned before. Not to say about the meteor, something like that, a lot of things. Okay, while steps are taken to predict the best positions, they can't be predicted perfectly at all the time due to the nature. Okay, and of course there are clock errors. Okay, so the satellites and receiver both need very good clock to do their job. Okay, the smallest error can throw off the range of measurement from the receiver and something like that. Okay, so what happened now? Clock errors is due to the time of due to the satellite. They uses the atomic clock, while the receiver they are using the GPS time. So there are some differences in between, and this also will affect. You know why? Because of the measurement multiplied by the constant is the speed of the light. Therefore, even a tiny differences will magnify the error. Okay, and the selective ability, as I said, the accuracy of GPS was intentionally degraded by the DoD, and before this due to the selective ability, the error is 100 meter. After it's being off by on the May 1st 2000, so what happened, it helped to increase the accuracy of the GPS. So basically the budget is like this. Ionosphere is about 5 meter, blah blah blah. Troposphere, you can see here, even though it's a microseconds, it gives you a meter scale and tends to give you more or less about 10 meters. But nowadays more satellites we have, such as using the GLONASS, BEDO and so on, so eventually it promotes the accuracy, and it gives us better accuracy than before. Okay, and for the application of the industrial approach of the GPS users, so the industry, most of them are using the differential corrections for the GPS, where GPS receivers on the ground, on the known location, it becomes base station, so it will put as a static reference point, and it will transmit the error corrections to other GPS on the local area, real time, or using the software. So the idea is the base receiver will using the wide land observations to increase the accuracy and eliminates those errors such as ionosphere, troposphere, ephemeris data and more, and those corrections being sent to the receivers that being used, the GPS that being used to collect the data on the ground on the real time, so it will increase the accuracy into a sub-meter range. Okay, and it is widely being used, so the surveyors are using this basically. And what happened, there are also a lot of the GPS sources. One of it is we are using the real-time kinematic as provided by this JUPEM. Okay, so it is a wide area augmented system in the real time, okay, and help to increase the accuracy by sub-meter degree. And how accurate is the GPS? Is basically the GPS that we use for the recreation is about 10 meter or 5 meter if for the new GPS. However, for the mapping and the survey grade is up until 2 mm if you are using the real-time kinetic and advanced survey methods with the software and so on. Alright, but for us, we don't really see we don't really look into the higher accuracy due to the nature of our field. Let's say you are using the GPS to collect the data for environment. Basically, the environment doesn't require too accurate GPS data as long as it can show us where those phenomena or those reading those data being collected. Same goes for the social science as well. We don't really there's an ethics saying that we can't give actual locations due to the infringement of the privacy. Therefore, it's good that we can give them idea of where the data be collected, but not too accurate, because we have to respect the privacy and also ethics in research. However, if you deal with the civil engineering, road engineering, you deal with these surveys, boundaries, so the accuracy is a must. Therefore, it's very important for you to understand the application, the how you call it, the actual nature of the field, and also how you can make use of this GPS as a tool for the data collections, and thus you can integrate it with the GIS. So what we do with this GPS GIS integrations is basically the ability to identify relationships between the features based on the locations and the attributes, where GIS allows the users to view relationship in maps, charts and more. So the examples, you can create layer of roads, traffic signs, accidents, buildings, and you can superimpose with different layers of relationship between the features such as the land use and so on, the population, crime rate and so on. Thus it will give you very rich informations to understand the phenomena happened with the attributes, and also the informations can support the evidence on how you interpret the informations. Okay, so once the data is collected on the GPS receiver, it can be directly transferred to the GIS system. Basically, nowadays you can just collect it with your phone, upload in the Google data, and also you download to your GIS, and you can have it with the pictures as well. So nowadays it's very easy for you to do this integration and so on. Okay, and GPS is a powerful tool to provide the unique positions. Okay, with these informations you can navigate back to it. However, you can relate this feature position to any other feature positions unless you standing on the side and the features are visible. Therefore, the GIS provide great analysis capability. Okay, but in order to do that, you have plenty of good data, and also a lot of data needs to be collected in order to allow the full capabilities of GIS being utilized. But nowadays, the GIS has been widely used by the government and also the private. So by getting to get the data is not really difficult as 10 years ago. When I'm doing my GIS thing, it's very difficult to get data. Nowadays it is easier. Okay, right, so you can read this one, right? And these are those GPS. Yeah, the one that you use during the field course is the handheld GPS. So they have the marine GPS, and these are the GPS. Okay, I don't have it because the price is about 200,000 ringgit. It's very expensive. And thank you very much for watching the video, and hope that you can understand from this topic. If you have questions on it, please let me know, and I will try my best to explain to you. Thank you.